Today we're going to talk about the binomial probability distribution and binomial probability experiments. A binomial experiment is a statistical experiment that has the following properties. 1. The experiment consists of n repeated trials. 2. Each trial can result in just 2 possible outcomes. We call one of these outcomes a success and the other a failure. The probability of success, denoted by lowercase p, is the same on every trial, and the trials are independent. That is, the outcome on one trial does not affect the outcome on other trials. We define the particular binomial experiment as follows. We use the parameter n to represent the number of trials of the experiment. We use lowercase p to represent the probability of success in one trial of each time we do the experiment. Q is always equal to 1 minus p. For the rest of everything we do in statistics, a Q is always 1 minus p, and it represents the probability of failure for one trial of the experiment. And X represents the random variable that represents the number of successes under consideration for the problem. But note that there can be more than one X for each problem. I'll explain this as I go through the problem that we're going to work on. So, as I already said, we define the at least parameters for the particular binomial experiment as follows, but then we also have something called the mean or expected value or expectation of the experiment, and that we just take n, which is the number of trials, times p, which is the probability of success for each trial. Now that only works for what we call binomial experiments. The variance is simply n times p times q, and the standard deviation is the square root of the variance, which is the square root of n times p times q. The probability of X successes in a total of n trials is the probability of X equals the number of combinations of n things taken X at a time times p raised to the X power. That means the probability of success in one trial raised to the X power, and then Q raised to the n minus X power. That is a long, complicated formula. And of course, we're going to use spreadsheets to take care of all of that. But this is the formula for it, and back in the day, we would have to plug all those things into a calculator for each thing that we're supposed to do. A recent survey asked Republican voters whether or not they were concerned about climate change. The results concluded that 47% of Republican voters seemed to be concerned about climate change. If 12 Republican voters are randomly selected, determine the expected number of those that are concerned about climate change. Well, the expected value is simply n times p, and we'll get to that on a spreadsheet. The variance of those that are concerned about climate change, and we can calculate A, B, and C very easily on a spreadsheet, so we'll come back to those. Let's look at D. the probability that 4 are concerned about climate change. That means 4 out of this 12 over here. Part D, what N, P, Q, and X are. N is the total number of trials. So the way I have this worded, N, for all of the problems for A through F, will be 12. P, as I said, is the probability of success on each trial. The experiment is randomly selecting a Republican voter. And each time I do that, there's a 47% chance that that person would be concerned about climate change. We don't write these things as percents, we write them as decimals. I hope you can easily convert 47% to 0.47. So for part D, N is 12, P is 0.47, Q is 1 minus P, and that would be, in this case, 0.53, because 1 minus 0.47 is 0.53. Now, X, that's the thing for this problem that will throw students off. For part D, we're wondering what the probability that 4 of those people who are selected, 4 out of the 12, will be concerned about climate change. So in this case, X is equal to 4. Now when we say the probability that 4 are concerned, we mean exactly 4. Not 4 or more, not 4 or less. We mean exactly 4. So for part D, N is 12, P is 0.47, Q is 0.53, X is 4. Let's take a look at part E. The probability that at most 5 are concerned about climate change. What that means is N is still 12 for this particular problem. P is still 0.47. Q will still be 0.53. X is going to be 0, 1, 2, 3, 4, and 5. Because at most 5 means no more than 5, but it could be 0, it could be 1, it could be 2, it could be 3, it could be 4, it could be 5. Let's look at part F. F asks about the probability that at least 7 are concerned about climate change. That's 7 out of 12, and it's at least 7. That means the least amount could be 7, which means 7 or more. So that would be either 7 would be concerned, or 8, or 9, or 10, or 11, or 12. Now you can't go more than 12 because we're only selecting 12 people for this particular problem. Also, we can't go below 0 because that would be meaningless. Let's head over to spreadsheet mode and see how we solve each of these. Here we are in spreadsheet mode. Let me remind you what the problem we're trying to figure out is. There are Republican voters. We randomly select 12. We know that each selection has a 0.47 probability of that person being concerned about climate change. So let's go to our parameters. First parameter is N, and that tells me how many times I'm trying the experiment. Since the experiment is randomly selecting a Republican voter, and we're running that experiment 12 times, N is 12. Now, according to the problem, each time we select a person, there's a 0.47 probability that that person is concerned about climate change. So that's 0.47. We don't have to put in Q because in a spreadsheet it will automatically calculate that for you. You just type it in as 1 minus whatever is in the cell B7. Also, the mean, the variance, and the standard deviation are all just simple calculator things, but why not have it on the spreadsheet? So the mean is simply n times p, so we just type in equals whatever is in cell B6 times whatever is in cell B7. In other words, just n times p. For the variance, it's a similar thing, except it's n times p times q, and I kind of did a little cheating shortcut here. Since the mean is n times p, we already have the n times p part, so all I did was take whatever the mean is, and then I multiplied it by whatever q ended up being. And now the standard deviation is just the square root of the variance, and we typed in equals. The function for square root is SQRT. And then we take the SQRT of whatever is in cell B11, and there we have it. Now, we're going to talk about binomial probabilities, and the random variable x, that's what we call this column, the random variable. I already stated that we can start off as low as 0 and work our way up as high as 12, but no more than 12. Again, if we're only selecting 12, we can't get 13 or 14 or 15 people that care about the environment, or global warming in this case. And we can't get less than 0 because that would be meaningless. So I'm going to just type in a 0 for the first cell. You can simply just number the next cell down as 1 and then 2 and 3, but we have a little bit easier way of doing that. Instead of doing it that way, we can use a function to keep adding to the next cell. And the way I do that is, after I type in the 0, I'll type in equals. I click on the cell right above, which is cell D4, and then I say plus 1. And now I'm going to click back on that cell and drag and drop that all the way down to until I see a 12. Whoops, I only went as far as 10. So let's go a couple further, and there we have it. So now we have all the possible outcomes that can occur. There can either be 0 out of the 12 on up to 12 out of the 12. It would be extremely unlikely that all 12 would be concerned about the environment given these parameters, and it would be also not so likely that 0 would be concerned. In fact, we can estimate how many will be concerned by taking a look at the mean. And this is what I meant when I said the mean is also called the expected value or the expectation. We would expect about 5.64 of these people to be concerned about climate change. Now, we can't have 5.64 people, So the most likely occurring thing would be somewhere between 5 and 6 people. It would be the most likely occurrence. Now, that doesn't mean that it'll be 90% or anything in a case like this. It's just going to be more likely than any of the others. I gave you a really long formula when we were going through the actual problem on how we calculate binomial probabilities. Now, I'm going to go through this using that long formula at first. So don't copy what I'm about to do yet. We're going to truly take advantage of the spreadsheet at some point, but just don't do what I'm doing at first. So let's go back to the problem and the formula. And here we have it. The probability of X successes in N trials is, and then we have P of X equals the number of combinations of N things taken X at a time, the probability of success in one trial raised to the X power, and then Q raised to the N minus X power. That's a pretty long formula, and I'm going to type it in the long way, and we will take it from there. So this is going to equal. We have a combination formula in the spreadsheet. Combine N things. So I'm going to click on this N. And when I do that, I have to decide, do I want that cell reference to be static or dynamic? In this case, it's static because for this problem, it's going to always be 12. Keep in mind, other problems, it will be different things. So I'm going to simply type a $sign before each one. I already went over what that means. It's a static cell reference. I don't want it to change. And then comma, the number chosen comes from the random variable. So for this particular cell, I want it to be 0. I'm going to close my parenthesis and say times, I'm going to open a parenthesis, and then we're going to take P, which is in cell B7. Then I have to decide, do I want that to be a static reference or a dynamic reference? And we always want that one to be a static reference. So I'm going to put the $sign before that. I am going to raise that to the X power. I'm going to close my parenthesis, times, which remember is Shift 8, open parenthesis, Q. I want that to be a static cell reference. Yes, this is long, so I put the $signs before that. And I am going to raise that to the, again, this is complicated, N as a static cell reference minus X, which is a dynamic cell reference. I'm going to close a parenthesis for the exponent, the Q raised to a power, and press enter. And there we have that number, which is a pretty small number. It's 0.00049, etc. Now I'm going to drag and drop all that down, and there we have it. If you look at the probabilities, this means the probability that out of all the 12 selected, that 0 of them are concerned about climate change. This number represents that exactly one of them is concerned about climate change. Now, if I look at 5 and 6 in particular, look at the probability there and compare it to all the other probabilities. All the other probabilities are less than whatever the probability of 6 is. Again, going back to the mean, that is the expected value, or the number of people about that we would expect who would be concerned about climate change if I selected 12 Republican voters. I'm going to get rid of all of these, and I'm going to do this by taking full advantage of a spreadsheet using a spreadsheet function. So be sure to watch the next video so you can see how we take advantage or take full advantage of the spreadsheet to do binomial probability distribution problems.